Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we'll be working on Unit number 4, Lesson number 14, on Newton's Law of Cooling. In the last lesson, we looked at compound interest, which was one excellent example of where exponential functions are used in the real world. Another one that the Common Core would like you to be exposed to is how liquids cool in a room that's held at a constant temperature. Now you might think, well, that seems a little bit limited. And yet, the cooling of liquids affects just about everything, including the weather, including global warming. Understanding how heat is transferred and how to model that transfer of heat is really critical. Now, obviously, it's also really complicated. We're just going to be scratching the surface today and seeing how we can modify an exponential function by using transformations in order to make it model a cooling liquid. So let's get right into it. Exercise number 1. Consider the decreasing exponential function f of x equals 8 times 1/2 to the x. Letter A says use your calculator to sketch the graph using the window indicated. So, why don't you go ahead and do that? I'm not going to pull out the TI-84 Plus right now. Why don't you put that function in, use the window indicated, and then I'll do a sketch as well. All right. Well, even without our calculator, we should still really be able to sketch this. Right? We know that its y-intercept is 8, and we know it's a decreasing exponential. So it looks something like this. All right. Letter B says clearly the value of y gets smaller as x gets larger. Does it ever reach 0? Okay, in other words, is there some x value, something you can put in here, that eventually will give us a y value of 0? Why or why not? Think about this. This is a very, very important question. And the answer is no. It gets very close to 0, but never reaches it. Because we always multiply by 1/2. The only way to multiply and get to 0 is if we're multiplying by 0. But even though our result will get very small, if we keep multiplying by 1/2, there's always going to be half remaining, right? So we go from 8 to 4 to 2 to 1 to 1/2 to 1/4 to 1/8 to 1/16, etc. Yeah, they're getting smaller, much, much, much smaller, but they're never reaching 0. But it does get very, very close to 0, right? It levels out, getting very close to the x-axis. Very important. All right? Pause the video, write down anything you need to, and then we're going to go on to cooling some liquids. All right, let's do it. I wish we had a temperature probe, a cooling liquid, all that, so you could really see this. But let's start off with some easy numbers. Let's assume that a liquid starts at a temperature of 200 degrees Fahrenheit and begins to cool in a room that is at a steady temperature of 70 degrees Fahrenheit. Now this is important, okay? The room is at 70 degrees and it's always going to be at 70 degrees. And what we're assuming here is that the room is very large compared to the liquid. Because quite honestly, if we took let's say a cup of coffee at 200 degrees Fahrenheit and put it into, let's say, a small cooler that was at 70 degrees Fahrenheit, then sure, the coffee would cool down, but the air in the cooler would heat up as well. We're not allowing that to happen in this room. We are just fixing the temperature of the room at 70 degrees Fahrenheit. Now letter A says draw a rough sketch of what you believe the liquid's temperature function looks like as time increases. Think about this a bit. Well, I definitely know that it starts off at 200. In fact, why don't I just label that right here? And I definitely know it's going to curve down, but, I don't think it can get any cooler than 70, right? So it's got to look kind of like this. Maybe I'll put even a dashed line there at y equals 70. Letter B, based on your graph from A and your work from exercise 1, why would an equation of this form, let me write y equals a times b to the t, not model this cooling well, assuming that b is between 0 and 1? So, like let's say we had something like this. Why would this not do a good job? And then how could we modify the equation to make it model the situation more realistically? Think about this. All right, well, this is pretty tough, okay? But if you've been really understanding what's going on so far, you'll have it, right? It won't model it very well because this function will approach y equals 0. But the liquid approaches y equals 70. So what we're going to do, right, so in other words, anything that looks like this, let me draw it in a different color, is going to end up having a graph that kind of looks like this. And yet we need to have it actually look like this, right? Where it kind of levels off at y equals 70. So what we're going to do to modify our model is we're going to make it into this, y equals a times b to the t, but then we're just going to shift it up. We're going to shift up, right? And that's what we're going to play around with for the rest of the period. So we take a normal exponential model and we're going to shift it upwards, and we're going to shift it up enough so that it's approaching that room temperature as time goes on. All right, pause the video now and think about what we did on this slide and write down anything you need to. All right, I'm going to clear out the text. And why don't we head back to blue? All right, exercise 3. Let's stick with the same cooling liquid we had before, i.e. one that starts off at 200 degrees Fahrenheit and cools down in a room that's held at a constant temperature of 70 degrees Fahrenheit. We will now model this cooling Fahrenheit temperature using the equation f of t, so F for Fahrenheit, equals a times b to the t plus c, where a, b, and c are all parameters, i.e. constants, in the model, and t is in minutes. Which of these constants is equal to 70, and why? Think about the last problem. So one of those three numbers, a, b, or c, is equal to 70, and which one? All right, well, c has to be equal to 70, okay? The vertical shift. All right, and c's got to be equal to 70 because a times b to the t, well, that'll head towards 0. But we need it to head towards 70. So a times b to the t plus 70, well, that will head towards 70 degrees. All right, I mean, if a plus b to the t is heading towards 0, then 0 plus 70 will be 70. Letter B, none of these constants is equal to 200. None of them. But t of 0 equals 200. What does this let you solve for? Because clearly the beginning temperature is 200. Well, right now this is my model. Right now my model is f of t equals a times b to the t plus 70. Okay, plus 70. So let me see what I can solve for. Let me put in 200 for the temperature. Let me put in 0 for time. Ah, look at that. B to the 0 is 1. A times 1 is 1. So this is going to allow me to solve for A. A must be 130. Now watch out for this. This tricks my students all the time. We've gotten so used to that number, that A, being the temperature we start at, or the principal amount of money we start at, or the population we start at. But that's because we didn't have a vertical shift. That is no longer the case. In fact, what will now be the case is that A plus C will always be what we begin at. Always be the thing that we begin at. Now, what's really cool is we now have this model. We have f of t equals 130 times b to the t plus 70. The only thing we don't know is b. And what do we need to figure out b? Well, it's simple. We need simply one additional point on the curve. Or, to put it another way, we need one additional time and temperature pair. So let me give you one in letter D. It says determine the value of B if the temperature after 5 minutes is 153 degrees Fahrenheit. All right. Well, again, right now our model is f of t equals 130 times b to the t plus 70. So what I'm going to now do is put 153 in for f. I'm going to put in 5 for t. And I'm going to solve for b. Now let's take a look at what we have. We've got b to the 5th times 130 plus 70. So the first thing I'm going to do is get rid of that 70. Right? And that's going to give me 83 is equal to 130 b to the 5th. Now I'll get rid of that 130 by dividing it on both sides. And I'll have b to the 5th equals 83 divided by 130. And now I can get rid of the 5th by either taking the 5th root of both sides, or better yet, let me raise both sides to the 1/5. So b will be 83 divided by 130 to the 1/5. Take a moment and make sure you can do that on your calculator, okay? All right. Well, when I work it all out, b ends up being 0.91. And that really gives us our model, right? We now have absolutely everything we need. Okay, I'll summarize the model on the next page, and we'll work with it a little bit more in this problem. But pause the video now and write down anything you need to. Okay, I'm going to clear this out. Or I'm going to try to clear it out. There we go. Let's keep going. There's that model. We got it all. We got the A, we got the B, we got the C. Letter E says, what is the temperature of the liquid after half an hour? After an hour? After 2 hours? All right. Well, why don't you use that function to figure out each one of those temperatures? And I guess round to whatever you think is appropriate. All right. Well, this is simple enough. The one thing we have to be careful about is that the T is in minutes. All right, so if I want to know what the liquid's temperature is after a half an hour, I have to put in 30. So that's going to give me 130 times 0.91 to the 30th plus 70. And I work that out, and I find that after 30 minutes, we're already down at 77 point, I took mine out to 3 decimal places for some reason, degrees Fahrenheit. After an hour, after 60 minutes, I'll have 130 times 0.91 to the 60th plus 70. That gives me 70.453 degrees Fahrenheit. By the way, notice how close I'm getting to room temperature. After an hour, my liquid, my coffee, let's say, that I had started at 200 degrees Fahrenheit is almost at room temperature. I probably wouldn't be able to tell the difference after an hour between the temperature of the coffee and the temperature of the room. And after 2 hours, it's going to be even more extreme. It's going to be basically the same temperature. 130 times 0.91 to the 120 plus 70 gives me 70.002 degrees Fahrenheit. So notice how it's approaching that 70-degree room temperature. Letter F then says, using your calculator, sketch the graph of the liquid's temperature. Decide on an appropriate window and label it on your axes. So go for it. See what you can do. All right, let's go through it. Well, to me, and again, I'm not going to break out the TI-84 right now. To me, right, you've got to have your Y window go up to at least 200, and you'll probably want it to go even more. Take a look. After 60 minutes, we're almost at room temperature, so putting our X window at 60 would be great. And then our calculator should give us something that looks like this. I think it's actually particularly helpful to also graph the line. That's supposed to be a horizontal line, y equals 70. But there's no absolute requirement of that. It didn't say to do it, but that's what our function's going to look like. Letter G, finally, it says to algebraically, we're going to have to really scoot this in, algebraically determine to the nearest tenth of a minute when the temperature reaches 100. So I don't know, maybe I like my coffee right at 100 degrees, right? So I'm trying to solve this particular problem algebraically. And let's do it. Think about it again. Taken 0.91, raised it to the t, multiplied by 130, added 70, and set it equal to 100. So I'm going to subtract the 70, and that's going to give me 130 times 0.91 to the t equals 30. I'll get rid of the 130 by dividing both sides. This is starting to get pretty old hat, huh? 0.91 to the t equals 30 divided by 130. And now to undo an exponential, I take a log. All right, I think I'll just stick with log base 10, but we could also go with the common log. Log base 10 of 0.91 to the t equals the log base 10 of 30 divided by 130. And since I'm running out of room, right, remember I'd bring the t out, divide both sides, and I'd have the log of 30 divided by 130, all divided by the log of 0.91. Whoops, that is 15.5 minutes. So I gotta let that coffee sit there for about 15 minutes before I can drink it, which is really unfortunate, but that's okay. All right, pause the video now, write down anything you have to, then we'll clear out the text and finish up the lesson. Okay. So we did some pretty sophisticated modeling today, and it really required you to understand that when you have just a normal decreasing exponential function, then it's always approaching a y value of 0. So if you need a decreasing exponential function to approach some other value, like let's say 70 degrees Fahrenheit, you have to vertically shift that exponential up by simply adding on what you want it to approach. So if I've got a room temperature of 65 degrees, I'd add 65 onto my function, shifting the entire thing upward and creating a new, better exponential function. Newton's law of cooling is really kind of cool. And again, not too hard to understand, but it is pretty sophisticated in terms of the level that we're at right now. So work at it, try hard on the homework, and I'm sure you'll get it. For now, I'd like to thank you for joining me, Kirk Weiler, for another Common Core Algebra 2 lesson. Until next time, keep thinking and keep solving problems.